So here we have this beginner's exercise for the shear force and the bending moment for this beam. So this is a topic where we want to find two things. One is called the shear force. Okay, so B is actually something called the shear force. Okay, it's gonna be in kilonewton, newton, pounds, or something. And also we want to find the bending moment. This thing is called the bending moment. So these are two different entities, okay? They are of different nature. One is the force, okay, we already know it, and the other is the bending moment, which, well, in international units, these things are in kilonewton meter, or maybe you have it in English units, pound feet, or maybe pound inches. Okay, so that's the thing. Now, the physical explanation of these two guys, shear force and bending moment, can be described. It's just a description, okay? It's not a definition. It's just a description because what we are trying to get over here is to how can we solve this problem, okay? It's not an idea of be very formal about the topics, not a theoretical part of this stuff. It's just to know how to find them, okay? What's the magnitude? What is happening to the beam regarding these two entities over here, shear force and bending moment? Well, okay, so having said that, let me just try to put you something. Okay, so if you break apart the beam, what you want to find is how is the shear force, which is the tangential component of a force. We already have seen something which is called the axial force, okay? It's along this length, okay? This thing is called the axial force. We see this mechanical effect when we talk about tension or compression. But now what we want to find is how this shear force, which is like kissing the surface of this over here. Maybe if you see this, let's just see this. Imagine that you have a block or something of something, okay? And you're trying to and you glue it to a table. So this thing, this block of whatever, it's glued to this surface, you know, a table, a stool, whatever you want to say. So it's glue, okay? And somehow you want to rip it apart by doing this. So try to do that, okay? So what you're trying to do is to actually produce a shear force to this surface below the block, okay? You're trying to rip it apart. So it's like you're taking off a band-aid from your skin, and that pain that you feel, maybe that little pain that you feel over there, it's because of the shear force. You are actually trying to say, hey, if you remove this stuff over here, it's gonna put a friction into this surface. So that is actually the meaning of the shear force. Now the bending moment can be described by this. So take a bar or a beam or whatever. And if you try to do this, okay, maybe you have two strong arms and try to move it over there. So this is a bending moment. You're trying to maybe rip apart this bar by doing like that, or like in jail. Remember those cartoons that you have bars in a jail, and somebody's strong enough so that instead of having this, you pass to this one. So what you actually did to this stuff, these bars were held here, these were held like that. So what you did over there, so the rover could just escape from it. Okay, so you just applied a bending moment, okay, to these bars. I'm going to erase all this stuff, okay, because it's not that relevant. But it's just a physical description of what these two entities are. Okay, so it's just an easy explanation. It's not a description. Okay, so please beware that it's not a definition. It's just a description of what are these. Let me just put it over here. So this is for the bending moment. What I'm trying to put over here, these two descriptions over there, is because of the bending moment, and this description was due to the shear force. Okay, so that's basically the idea. Our problem. Let's go back to our problem. Meanwhile, I'm erasing this. So let's go back to our problem. Our problem is a beam. This beam is held by a pin support and a roller. The pin support is located at the left tip of the beam, okay? So let me just write it. So here you have a point A, a pin support, and here you have a roller. In between, okay, in between, I'm gonna put some measurements over there, but in between you have a 20 kilonewton going down, okay? So what we are trying to find out here is a drawing. These drawings are called diagrams. So we wanna find out the diagram for this shear force happening, for the shear force happening along the beam, all along the beam, not just in one point, but in all of the points from this beam. So let me just say that all this stuff, all the length of the beam, it's around 5 meters. It's 5 meters. And from here to there, you will have 1 meter, okay? I'm just making up some numerical values so we can solve this numerically and you'll be fine with it and you analyze it so it's better, okay? And so instead of dealing with letters or variables, so we're just still dealing with numbers over there. Well, okay, so we have formulated our problem. Let's just start by doing something that I call equilibrium 2D. The idea is to find the unknowns at A and at B. You need to find those unknowns. Maybe from some topics out of this one, you remember that a pin support has an AY and it has an AX. Those are the unknowns for this type of support. And for the roller part, you have an, well, okay, let's just do it in the most proper way that I can think of. So for that one, you will have this normal at B, okay? But do not forget about this 20 kilonewtons acting 1 meter from the left tip of the beam, okay? So this is your free body diagram, okay? This is a typical thing to do when you're working in statics, free body diagram. Now that you have that, let's just work out the equations. I'm going to start with the x part. The x part will tell me, okay, this is the meaning of forces at x. So the force at x will be ax equals to 0. Let's go for y. For the y part, I have ay going up. I have the normal going up, and this 20 is going down, so it could be a minus 20. But I'm going to put it in the other part of the equation, the right-hand side of the equation, which is a 20 positive. Okay. Now let's just move on to the moment. I'm going to do moment regarding A, okay? So moment regarding A, I cancel these two forces because they are passing through the point A, so they won't produce moment. And therefore, the 20 and the MB will produce moment. So let's just do the 20. So 20 times the distance. So maybe you see here, it's pretty obvious that I need to walk 1 meter to find that 20 perpendicularly. That's the whole point of the scalar method for finding moments. And according to 1 meter, so according to my right-hand rule to describe which one is the sign of this moment, it's going to be a minus and then a plus. Remember, the whole deal was 5 meters. Okay, so I need to walk 5 meters in order to find the normal force acting at B. So acting at B, I have a normal force going up. Why? Well, because it's a roller. And then what? Well, the roller just has one unknown, which is the normal of this roller, times 5. Okay, so this thing should be equal to 0. Now you have one unknown, so you can actually solve it. Let me just do my thing. You divide everything by 5, and I will divide this by 20. Therefore, you have that MB equals to a 4. Okay, so it's a 4 plus kilonewton. With that information, you can go now to the Y equation and get that AY equals, maybe it's not that difficult for you to get that this thing should be 16 kilonewtons. Okay, so, and what about it? Well, this guy was 0 kilonewtons from the beginning. Okay, so you have found yourself this stuff. Okay, so now you know what are the unknowns at A and at B. This is not the way. This is the first part to get the shear force and the bending moment. We haven't said anything. We haven't said anything about how to get the shear force and the bending moment. So we're gonna do that. Let's just see how many sections should we do here in order to find how many sections we will have in order to break this beam apart. Why should we have sections? Because otherwise we cannot see what is happening in the inside of the beam regarding shear force and bending moment. That's why we do the section. So this is a criteria, okay? Maybe there's a better way to explain this criteria, but I'm gonna say it. I'm gonna say this. This beam support, this 20 kilonewtons, and this normal here are disturbances that affect the mechanical condition of the beam, okay? So AY going up here, this 20 going down, and this normal going up, they will affect the mechanical condition of the beam. Therefore, those are disturbances affecting the condition of the beam. And you will say, okay, so I got it. Now what? Well, now the criteria, my way of saying this criteria of putting section is put one before and after a disturbance. So let's start with this pin support, okay? This pin support, if the criteria says put one before. If I put one before here, well, there is no beam there, so it's just trivial to put one thing over there. So, okay, so I won't put one before the pin support, but I can put one after the pin support, whoop, like that, okay? So let me just erase it because it was just dumb, but it was part of the criteria, okay? Is that it? Well, let's just go with this other disturbance. Put one before, got it. You already have that one. So this is section 1. And let's just put one after that. Okay, so I'm gonna put it over here. So this is gonna be section 2. Did you end this problem? Well, let me just see about this other disturbance. What about the normal? Well, the normal is another disturbance. Put one before. Got it. I already have this one. I don't need to put another one. Hey, what about after the normal at B? Well, if I put one over here, it's just dumb because I don't have beam over there. Therefore, in summary, what I have put over here is that I have 2 sections in order to analyze completely the whole length of this beam. That's what I have put over here. Therefore, what you need to do in this type of analysis, you do section by section, okay? So you try to solve this stuff section by section. Let's just start with section 1. I'm gonna use another color because, you know, I'm so bold at this creative part. So let's just use the analysis, the blue for the section 1. Okay, so I'm gonna do section 1. Section 1 will look like this. What are you putting? I'm putting a chunk of the beam. What chunk? The left part of the section 1. So you're doing this, I'm doing this. This is what I'm putting over there, like a chunk. Oh, so the section is put right at the middle of 1, right? No, it's not put right at the middle of 1. So where this thing is put, it's between A and the point where this 20 is located. Oh, so you mean by at the half of it? Why would it be half of it? It doesn't have any meaning to put it at half of it. I'm just putting in between these 2 points. This section 2 is gonna leave, okay? It's gonna leave between this point and this point over there. Oh, okay, so what I'm putting over here is that I'm looking at the left part of this section 1. So I will look at the point A, this is point A. Therefore, I will see the AY, but I already know how much is the AY, and I will put 16 over there. Fine, and what else? Well, nothing else, nothing else. What about the 20? I don't see the 20 because I'm looking at my left of the section 1. Oh, where the hell would I will be seeing, when will be seeing the 20 kilonewtons? Well, when I will do section 2, I will see these 20 kilonewtons acting on the beam, okay? So far, I won't see the 20 kilonewtons. What I will see in this section over here, in this chunk of this tip, I will see the point O, that's the typical way to call it. I will see a shear force there, and I will see a bending moment, the M over there. These 3 guys, O, V, and M, needs to be put all the time that you do a new section, okay? All these guys are gonna appear. These are actually your unknowns for these drawings. You actually want to know what's the behavior of shear force and bending moment along the beam. And this free body diagram, this is actually a free body diagram for a chunk of a beam. This chunk will actually let you look at what is happening all along this beam, okay? So more new stuff. All this beam measures X. You don't know the actual length of this chunk. It's just X. Why wouldn't I know this stuff? Well, because you're going from A to some point here. So in the middle, no, again, why in the middle of the 1 meter? You actually don't know. It's just a variable, it's just X. Well, okay, fine. What next? What next is that you will do X. If you do the X part, what do you mean by X part? I'm just summarizing that this is force at X, and force at X, you will see nothing actually equals to nothing. So 0 equals to 0. There's no guy, no one is doing something laterally. Okay, so 0 equals to 0. And what about y? Well, I have a 16 going up and I have a shear force going down. Okay, why is this guy going down? Because of tradition. Just because of that, just because of tradition. Can I put it up? Yeah, you can put it up. There's nothing in physics that said no. You should always put it up, or you should always put it down. Just like this moment over here, I put this moment in the positive part, but you can actually draw it in the other way around. There's nothing in physics that will tell you this guy always needs to be going down, and this guy always needs to be rotating positively according to the right-hand rule. So, but it's just tradition, okay? So 16 minus b equals to 0. When you move, you move, yeah, this section is actually trying to sweep from this point to this other point. So you're actually doing a sweep over there from 0 till 1. So you're gonna move from 0 till 1. Okay, so from 0 to 1, what's this equation? Well, maybe you see this at 16 equals to b. And you need to compute this equation from 0 till 1. Well, just a constant. Okay, so try to draw a constant. So at 0, you're at 16 kilonewtons, and when you hit 1 meter, right at this limit, when you're hitting there, you're still 16. Fine. So it's the most simple equation that maybe you have ever found yourself with. And these little lines that I'm putting over here is just for rendition purposes. What it means is that the shear force that's gonna be felt by the beam all along from 0 to 1, the magnitude is just 16 kilonewtons. Okay, fine. And then what? That's it for this part of the section. That's the information that this section 1 is telling you regarding the shear force. Let's see what about the M. So now you need to do moment regarding, you can, but the better point the best point to find the moment for this analysis is the O point. Why? Because you will delete the shear force, so you don't get into trouble. Okay, so let's go with this. And what we find over here is that, maybe you see it, 16 is not being applied at O. Okay, so I would see a 16 times X, because you need to walk X in order to find this 16. And it's going to be a minus according to your right-hand rule. And then what about B? Oh, nothing about B, just 0. Yeah, the moment produced by B at O is actually 0. And what else? Well, this bending moment, which is going to be positive, equals to 0 when you move from 0 till 1. Okay, so that hasn't changed. Section 1 just moved from 0 to 1, 0 to 1. Now you see an equation. This is actually a straight line equation with a positive slope, because you pass this minus as a positive when you go to the other way. Therefore, this should be a 16x when you go again from 0 to 1. So now let's just compute it. If you put a 0 at x, this guy will give you 0, okay? 0 what? Kilonewton meter, if you want to be more explicit. And when you put a 1 over there, it's going to give you 16 kilonewton meter. So what you are looking here is that it's actually ramping up. This bending moment starts at 0, okay? And then it starts increasing. The value starts increasing till you hit 16 kilonewton meter. It's different from this 16. Okay, it's not this 16. This 16 is units are kilonewton. These units are kilonewton meter. These guys are of different nature. Okay, well, okay. So you have the bending moment that is going to increase from 0 till 16, and the highest value for this part of the section 1, is actually 16 kilonewton when you hit 1 meter. Okay, that's what the information is telling you. Okay, good. Then what? Well, Then you will do another section. Oh yeah, you're right, another section. So let me just use green for section 2. Now I'm gonna analyze section 2. And this is the method, okay? The method tells you, do another chunk, buddy. And you still start at the left tip. Hey, why not the right tip? You can do it. You can actually do it from the right tip. But tradition, or at least my way of doing it, I always pick up the left part of every section that I do. So the section two, I always look at A. So I always look at A. So if I do section 3, 4, and whatever, okay, so in another examples, I will always look at the left part. Okay, and you will say, well, when the hell are you gonna see this normal over here? And the answer is pretty easy. I won't. I will never see this normal B. And you will say, so it doesn't really matter what I put here at B because I'm not taking this into consideration. Yeah, you're already gonna put it into consideration. You will see why later. Okay, so I'm gonna move myself over here and let's just put things that we already know. This 16 is going up. This is still X, okay? Every chunk that you do, the length is X, it's a variable. You actually want to get equations, okay? So you have yourself here an equation depending on X. So you wanna have, again, equation for X. O, and then B, and then M. So pretty standard stuff. Every section that you do, you need to put O and B and M. And now, surprise, surprise, you need to put the 20 kilonewtons. Why? Because now you can see it. If you are here at section 2, you will find out that at your left, you will see the 20 kilonewtons. That's what you did 2 sections. 1, because the 20 hasn't arrived yet, and 2, because the 20 has already been felt by the beam. So you need to analyze that change in the beam due to these 20 kilonewtons acting on it. Well, that's it. Yeah, that's it. So let's just do our equilibrium. This is a free body diagram for what? For another chunk of the beam. When you see, or when you already put the 20 kilonewtons acting on the beam. So X gonna be 0 equals to 0, and then Y, let's just go for the Y part. The Y part tells me that 16 is going up, minus 20, okay, because this guy is going down, and then minus B equals to 0. So this equation, I'm gonna pass this guy over there, so B equals to minus 4 kilonewton, okay? When you go now from, hopefully it doesn't surprise you too much, when this section is actually sweeping from 1 till 5, okay? Now the home of this section 2 starts at this point and ends here. That's where the domain of section 2 is. It's residing there at from 1 till 5 meters, okay? So this guy's, you know, it's meters. Therefore, you can actually go to your drawing board for the B part. And for the B part, take a look at it. You were living at 16, 16, 16, and then comes a 20 and pushes you down to minus 4, okay? This is minus 4. And then you go all the way as minus 4. How do you know all the way? Well, because this guy doesn't depend on the length. It's just minus 4 all the way till the end. Okay, so minus 4, minus 4, minus 4, minus 4, minus 4. And then, hopefully you see this, but the roller comes in and pushes you up 4 kilonewtons and leaves you at 0. Okay, this gap, this little gap over here is 4 kilonewtons. It's the roller that pushes you up till you get to 0. Okay, so everything is in equilibrium. Oh, that's when the roller does something to the analysis. You were at 16, you were actually at 0. Hopefully you see this, but you were actually at 0. And then comes the pin support, immediately comes the pin support, the vertical part of the pin support, and pushes you up 16. It's already here. So it pushes you up 16 and then leaves you at 16, 16, 16, 16, 16, and then comes a 20 and pushes you down 20 kilonewtons. All this gap that I'm putting over here is actually 20 kilonewtons. So that's why you were at 16 and then you are left at minus 4. So you go all minus 4, minus 4, minus 4, minus 4, and then comes a roller, boom, pushes you up till 0, okay? So you began at 0 and you ended at 0 for the shear force, okay? So that's what the shear force, that's what is happening to this beam. Okay, you will need to be careful if you are designing some material or putting some load into the beam. Hey, what about which one is the point that has more probability of breaking? Okay, which part of the beam is more fragile, or maybe you want to find out what's the biggest load that I can put as a point for into this beam. Well, I don't know about the material, but I know about the shear force. And the shear force telling me, look, guy, you need to be careful over here, because this 16 is actually the highest shear force experienced by this beam. Hey, what about this -4? What about the negative? Oh, the negative is just telling me that it's the other way around. So the shear force, instead of going down, it's going to be going up. Okay, because our traditional way to put it is like going down. So if I find a positive, it means that it's actually going down. The shear force is going down, 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 down. It doesn't really matter if it's up or down, okay? It's just the magnitude what it matters to us. But what it's telling me that it's going down, 16 is going down, 16, sorry about the confusion about up or down, but it's actually what is happening. And what about this -4? It's telling me that it's actually the shear force going wrong. So if I see a minus, okay, like this, if I see a minus over here, it's telling me that what I assume it was, like going down, it's actually wrong. So it's actually going up. The shear force is actually going up. It doesn't really matter. This drawing is telling us that you need to be careful about from the 0 till 1 meter. From 0 to 1 meter, you need to be careful because it's the highest shear force that this beam is feeling. Okay, well, okay. So that's the explanation, or at least a physical description of what is happening inside the beam regarding an entity called the shear force. Now let's just go back and see what about the bending moment. So the bending moment, let's just put it here. We're gonna find out when we do the moment regarding O. Okay, so what we have over here is okay, so 16 times x. Again, why? Because this length of the chunk is still x. It's going to be a minus. Okay. Now, what about the 20? Well, the 20 is producing moment regarding O because it's not passing through O. So you will put 20 times a distance. How much is this distance from here to there? From here to there, how much is this distance? Because this is the distance that you need to walk. Well, there are several ways to find it, but the easy for me, maybe, you can see that I can go all x, all to the left to this tip, and then go back something that I already know, which is 1 meter. So I'm gonna go all x and then subtract 1. This is actually x minus 1. Okay, so this is, let me just rearrange it so you don't have a problem reading this. Come on, reading this one. So I'm gonna put it over there. So 20 times x minus 1. Okay, and this is actually a plus because it's trying to move it around like that. Okay, plus m. Okay, do not forget about this variable, which is we want an expression for this m. Okay, and this thing is equal to 0 when you move from x equals to 1 to x equals to 5 meters. Okay, again, meters. Therefore, what you will get over here is m. I'm going to pass this guy as positive the other way around, so 16x. And I'm going to pass this positive guy all the way up to the right hand as minus, so minus 20x minus 1. Okay, my suggestion is to leave the parentheses. Try to leave the parentheses because it will be easier to see zeros. Let me just tell you what I mean by that. So now you need to compute this equation when this thing is 1. Okay, so when you put a 1 in the x part, well, maybe it's easy to see that this term here is going to be 0. Therefore, I'm leaving with a 16 kilonewton meter right at 1, which was this same value. So what it tells me is that the ending of section 1 is actually the beginning of section 2. Oh, okay. So that happens all the time? No, it doesn't happen all the time or for all circumstances, but it happens here. So it's a good way that something is happening in the right way, okay? Well, okay, so M1. Now, what about the other point? The other point is the final point of the beam, which is the 5. So if you apply a 5 over there, you will stuck with 16 times 5, okay, minus 20 times 4, because 5 minus 1 is a 4, okay? So you can do the algebra. This is my way of doing this. So it's 4 times 4 times 5, okay? Let me just put it like that because I don't use calculator, okay? So big boo for me. And this thing is actually a 5 times 4 times 4. So maybe you see now that this guy is actually the same one here and the same one, but with a minus sign. Therefore, this thing equals to 0. So those are good news. That you get to a 0 at the end of the beam is good news because you got to equilibrium. Now, it means that you started at 6, okay? The beginning of your section 2 started at 16, sorry, not 6, but 16 for the moment, and you ended at 0 for the moment. So how can you join these 2 points from here to there? Well, let's go back to the equation. And the equation is telling me, look, this is the way that I'm gonna move from 1 till 5. So what's the name of this curve over here? You need to apply some of the geometry that you have in from other courses, and you will see that this guy is a straight line, but with a positive slope or with a negative slope. Well, you can apply logic and say, well, if I'm at 16 and I need to get to 0, I need to go down, right? So it needs to be a negative slope. Okay, something like that. This is just for rendering purposes. Most of the books does it, but you shouldn't. It's not that relevant if you need. These guys are not like areas, okay? Okay, so maybe you see this, maybe you see it, but it was a negative slope because you have 16x and minus 20x, okay? So you have a competition between 16x and minus 20x. This minus is gonna win. So you will end up with a minus 4x. Okay, you will end up with a minus 4x. Therefore, it's a negative slope for the straight line. That's what I wanted to tell you. Okay, you don't need to do all this analysis, but it's a good way to know that you are in the right path because this guy will lead you from 16 till 0, and that is the ending of the problem. Okay, now some part of lessons. Look at it. When the shear force crossed the value of 0 for shear force, which is happening at 1. So you started here at 16 and you end up at minus 4. So there is a point, 1 meter, where the shear force just crossed the 0 value, okay? So it seems that right there, you have a maximum for the bending moment. So you need to be careful. It's not that you need to be careful, okay? But you need to be aware that when the shear force gets to a value of 0, you will have a maximum or maybe a minimum for the bending moment. And those are points that of reference. You need to be aware of those points because there's something telling you maybe this thing is gonna happen, something for the beam, or maybe I shouldn't load too much. I shouldn't put a 20 kilonewton over there because maybe this guy fails or the material fails or maybe it just breaks up. Those things are part for another more complicated analysis. But because you need to know about the material of this beam, but nonetheless, you already have some tools for design. Okay, so you already have some tools to say, well, maybe I should be careful about when this thing is about 1 meter because maybe the shear force is too high from 0 to 1, or maybe I have a maximum bending moment, which is the value is 16 kilonewton meter, right at 1 meter. Okay, so those are questions that you can start answering just by doing this simple type of analysis for the shear force and the bending moment, okay? So that's what I wanted to tell you regarding this example. Okay, so see you guys on the next